In video 42 of Tensor Calculus, we'll follow up our previous video with trajectory examples in each of our sample coordinate systems. We'll start with Cartesian coordinates. The first thing we want to do is to establish an expression for the position vector. And to accommodate that, I've drawn this little diagram of Cartesian coordinates. We have the three axes, x, y, and z. We have the position vector r in blue here, and the basis vectors x hat, y hat, z hat, as you see them here. Okay, now what we're going to do is to construct a vector that runs along the x-axis from the origin out to this point. It has a length of x, and it's in the direction of x hat, like so. Then there's going to be a vector that we construct here, parallel to the y-axis, for a length of y, and it's in the direction of y hat. And again, a vector this way, vertically, and it's going to be z times z hat. Okay, so if we add these three vectors together with vector addition, this one, and this one, the result is going to be our position vector r. So that leads us to this expression. You can see how we're adding each of the vectors we've constructed here to form the position vector. Okay, next thing we'll do is to derive the velocity and acceleration expressions. And for that we'll use the tensor calculus formulas we derived for the velocity vector components and the acceleration vector components. So for velocity, all we're doing is to take each of the coordinates, the derivative of each of our coordinates with respect to t, and we'll use those values to form a linear combination. And that's what we have here. We're simply taking the time derivative of x, y, and z one at a time, combining them with our basis vectors to form a linear combination. And that derives from this expression right here. Okay, for the acceleration, it's similar, but the expression is more complex. However, in Cartesian coordinates, we know that there are no Christoffel symbols. All the Christoffel symbols are 0. Therefore, this expression drops out of this formula for Cartesian coordinates. So the acceleration components is simply the time derivative of our velocity components. So we'll take the time derivative of each of these components and use those to form a linear combination, and we'll get this as a result. We see the second derivative of x with respect to t, second derivative of y with respect to t, and so on. And each of those components, combined with our basis vectors, give us the vector for acceleration in Cartesian coordinates. And it's that easy. Okay, let's move on and look at affine coordinates. Again, we'll start by deriving an expression for the position vector. And on our diagram, we've got the u-axis running horizontally and the v-axis running this way at a skew angle of alpha. And I've also written down the basis vectors z1 and z2. z1 basis vector is parallel to the u-axis, and z2 basis vector is parallel to the v-axis. So this time we'll construct a vector that starts from the origin and goes to this point, and that's going to be equal to the coordinate value of u in the direction of the z1 basis vector. And then we'll construct this vector up here, which is of course parallel to this, and it's going to be equal to a length of v running in the z2 basis vector direction. So if we add this vector with this one, we'll come out with our position vector right over here. So we're adding the two vectors that we constructed together to result in the position vector. All right, so next we'll look at velocity and acceleration. And again, the velocity vector components are simply the time derivative of each coordinate. So we combine those with our basis vectors here to form the velocity vector. It's that easy. We always, no matter what the coordinate system is, it'll always start by looking like this. The velocity will be the linear combination of the time derivative of each of our coordinate variables combined with our basis vectors. All right, for acceleration, this time again, the Christoffel symbols don't exist. They're all equal to 0, and therefore this term does not apply for affine coordinates. So again, the acceleration vector is just going to be found by taking the time derivative of each of these components and forming a linear combination. And that's going to look like this. So here you see the second derivative of u with respect to t, the second derivative of v with respect to t. And those then are the trajectory objects for affine coordinates. Okay, next we'll look at plane polar coordinates. Well, here our diagram shows that we have the polar axis running horizontally from the origin, here in black, and our position vector is the blue vector up to the point in our space, the position vector r. And this time the expression for the position vector is really easy because we only have one vector to construct, and it's the position vector itself. This vector has a magnitude of r, and it points in the direction of z1. So the position vector itself looks just like this. There is no z2 component to our position vector because the position vector is always parallel to and points in the same direction as z1. Okay, the next point I want to make here is that it's also very easy to normalize this expression because z1, this basis vector here, is actually a unit vector. So we can simply replace z1 with r hat and come up with the normalized form for our position vector. All right, so now let's look at the velocity and the acceleration. We'll again fall back on our formulas from tensor calculus. The velocity vector is really simple. As always, we simply take the time derivative of each of our coordinate variables, combine them with our basis vectors to form a linear combination. Now, it's important to mention at this point, a common mistake here is to just assume that the velocity consists only of this term. Since the position vector doesn't have a z2 component, it's very tempting to expect that the velocity is limited to the z1 component as well. But that's not the case. The velocity may well include a theta component. Just because r always points in the z1 direction doesn't mean that it's moving in the z1 direction. It could be moving in the z1 or the z2 direction or combination of them. Okay, next let's normalize this. And this time we can replace z1 with r hat, but z2 is not a unit vector. You'll remember that it has a magnitude of r, so we replace z2 with r theta hat, then we'll get this expression. R times theta hat is equal to z2. So the act of normalizing this expression adds a factor of r to this second term. And this is the expression that most people recognize for velocity in plane polar coordinates. All right, now we'll derive the expressions for our acceleration components. This time we can't ignore this term because our Christoffel symbols are not 0. We've got these guys to work with, so we have to employ these values into our expressions. All right, so let's just expand them out. we're going to have two expressions here. I is a free index, so we're working in a two-dimensional space. So we'll have A1 and A2. And A1 is going to consist, first of all, of the time derivative of V1 plus any terms where the Christoffel symbol has a value of 1 in the upper position here. So any Christoffel symbol that is non-zero and has a 1 in the upper position is going to have to be included in this expression. And there's only one of them right here. So we're going to have that expression, which will be gamma 1, 2, 2. And according to our formula, when j is 2 and k is 2, then we're going to have V2, V2. Now we can ignore the terms where gamma would be equal to 1 with 1s in the lower position, or 1, 1, 2, or 1, 2, 1, because all of those are 0. This is the only non-zero Christoffel symbol with a 1 in the upper position. So that's going to be our expression. Okay, so let's expand that out now. So we would have A1 is equal to the time derivative of V1. Well, V1 is just dr dt, so this first term is going to be the second derivative of r with respect to t. And then we're going to have this second term, which will be the Christoffel symbol, which is a value of negative r. And then times V2, well, V2 is d theta dt. And since we've got V2 twice, we'll just square that expression right here. And that's the proper expression for the the A1 vector component of acceleration. All right, we'll work on A2 now. A2 will be equal to the time derivative of V2 with respect to t here. And now we have to include any Christoffel symbols with a 2 in the upper position, and there are 2 of them. So we'll have gamma 2, 1, 2 times V1, V2. These upper indexes here correspond to the lower indexes here because they're dummy indexes, as you see in our expression. And then we'll have the second one, which is gamma 2, 2, 1 times V2, V1. But of course, we can flip these two indexes, and we can flip the order of those two expressions, those two factors. And when we do, we see that this term is exactly identical to this one, so we can collect those into a single term. So we'll do that. We're going to have A2. It's going to be equal to dv2 dt. Well, v2 is d theta dt, so this is the second order derivative of theta with respect to t. Then we're going to have two of these expressions. It's positive, and the value of our Christoffel symbol is 1 over r times v1. Well, v1 is just dr dt, and v2, which is d theta dt. Those then are the proper expressions for the acceleration components in plane polar coordinates. And you see those right down here. We see this expression right here and this expression right here. Okay, and finally to normalize it, as before, we can replace this with r hat and replace this with r times theta hat, giving us this expression. This expression is the same as this one. The terms are equal. But here we pick up a factor of r, and this factor of r here drops out of this expression. So these then are the proper expressions for the acceleration vector. in plane polar coordinates. Now, it might be very tempting at first to think that the acceleration is simply the second order derivative of this expression, meaning that we'd have just these two terms in our expression. But you can see that our derivation here proves that that is not the case. We have to include these other terms because the Christoffel symbols are non-zero in this case. So it's not as simple as it is in Cartesian coordinates to simply take the second order derivative. These expressions will involve the second order derivative, but they'll also have these extra terms to accommodate the non-zero Christoffel symbols. All right, with that, let's move on then to cylindrical polar coordinates. Well, here you'll remember that we locate points in space in cylindrical polar coordinates with the coordinates rho, phi, and z. Rho is the distance from the polar axis perpendicular out to the point. Phi is the angle that this little door swings at here. And z is the distance above the xy plane down here. So this time, to find the expression for the position vector, we'll construct a vector going up this way, which will have a length of z and points in the direction of the z3 basis vector. And then we have another vector that moves out this way. It has a length of rho, and it points in the z1 direction. Now our position vector does not have a z2 component because we don't need that to locate it. We just need these two vectors combined together to establish our position vector. So that's what we have right over here. We've got each of the two vectors. We have this guy here and this one right here. So that's our position vector. Okay, and to normalize it, we recognize that both z1 and z3 are unit vectors. So it's very simple. We just replace z1 with rho hat, z3 with z hat, and we've got our position vector in normalized form. Okay, let's move on to velocity and acceleration. And as always, the velocity vector is just a matter of forming a linear combination using each of our components derived respectively with respect to t. It's just a linear combination of each of our coordinate variables with respect to t combined with our basis vectors. And when we normalize it, this time we pick up an extra factor of rho here because the z2 basis vector is really rho times phi hat. The other two basis vectors are unit vectors, so they just transfer over as you see it here. All right. So finally we deal with acceleration. And as before, we have to use the full formula because we have these Christoffel symbols out here that are non-zero. So I think maybe this time we can just do it by inspection. Let's see. We'll start with A1. And A1 is going to be the time derivative of V1. V1 is d rho dt, so this is going to be the second derivative of rho with respect to t. And then we're going to have to add a term for each Christoffel symbol that has a 1 in the upper position. Only one of those, minus rho. And the lower indexes are 2 and 2, so it'll be V2 and V2. V2 is d phi dt. We've got two factors, so we'll square it. All right. A2 then is going to be equal to dv2 dt, which is the second derivative of phi with respect to time. And then we're going to have to add the term for each Christoffel symbol with a 2 in the upper position. There are two of them, but they're going to be identical because we can swap the indexes. So we're going to have plus 2, And the value of the Christoffel symbol is 1 over rho. And then the components are going to be V1 and V2. V1 is d rho dt. And V2 is d phi dt. And finally, our third component is going to be equal to dv3 dt. Well, that's dz dt. So that's the second derivative of z with respect to t. And this time there are no Christoffel symbols with a 3 in the upper position, so this term stands alone. All right, and those should be the components of our acceleration. And that's what we see right here. You see this term is here, this term is here, and this term is here. Okay, and to normalize it, as before, we're going to have to, these are unit vectors, but in this case we have to add a factor of rho to normalize it, because z2 is equal to rho times phi hat. So this term's the same as this is the same as this, but here we pick up a factor of rho and we lose this factor in the denominator down there. And so those are the results for cylindrical polar coordinates. As always, they look very similar in nature to plane polar coordinates. All right, and finally we'll switch over to spherical polar coordinates. This time the position vector is really easy because it always points in the same direction as our basis vector z1. It has no z2 nor z3 components. So our position vector just looks like this. It's the magnitude times our basis vector z1. Okay, well, we also see that z1 is a unit vector, so it's easy to normalize this thing. All we do is replace z1 with r hat. They're both unit vectors, so that's the normalized form. That's easy. Okay, well, let's move on now and look at the velocity and the acceleration. Velocity is just the time derivative of each of our coordinate values one by one, so that's easy. This is the value for velocity. The time derivatives of our coordinate values here forming a linear combination. Very straightforward. Okay, now to normalize this, we recognize that z1 is a unit vector, so we can replace it with r hat. z2 has a magnitude of r, so this will be r theta hat. And z3 has a magnitude of r sine theta, so we can replace it with r sine theta phi hat. And when we do that, we get the normalized form that looks like this, factor of r and r sine theta added to normalize the result. For acceleration, we just make use of this formula. There are going to be 3 acceleration components, so we'll start with a1, and that's going to be equal to the derivative of v1 with respect to t. That's just the second derivative of r with respect to t. Then we need a term for each Christoffel symbol with a 1 in the I position, and there are 2 of them here. There's gamma 1, 2, 2, gamma 1, 3, 3. So we'll have minus r. And this will be times velocity components v2 and v2. v2 is d theta dt. And since there are 2 factors, we'll just square this term. And then gamma 1, 3, 3 is minus r sine squared theta times velocity components v3 and v3. v3 is d phi dt, and again there are 2 of them, so we can square this term. And that's the expression for a1. a2 is dv2 dt. Well, that's the second derivative of theta with respect to t. And then terms for each gamma value of 2 in the upper position, and there are 3 of them, 2 here and 1 here. These 2 are equivalent because we can flip the order of the indexes. So we'll make this 2 times gamma 2, 1, 2. So this is 2 over r. And velocity components v1 and v2. v1 is dr dt. v2 is d theta dt. Then gamma 2, 3, 3 will be minus sine theta cosine theta times velocity components v3 and v3. That's d phi dt, and there are two of them, so we'll square it. And finally, a3, that's going to be equal to the derivative of v3 with respect to t. That's the second derivative of phi with respect to t. And then all the gamma terms that have a 3 in the upper position. There are two of them here, two of them here. These are equivalent, so we can combine them. So here we're going to have 2 over r times velocity components v1 and v3. That's dr dt and d phi dt. And then this guy is going to be, again, there are going to be two of them because they're equivalent terms here. We can flip the order of the indexes. So there'll be 2 times cosine theta over sine theta, and velocity components v2 and v3. v2 is d theta dt, and v3 is d phi dt. So with that, we have the acceleration, and it looks just like this. You see each of these expressions, one by one, are the components in our acceleration vector right here. Okay, I hope you can appreciate the utility of using a formula like this. The results are rather complex, but the process is very straightforward. You know, there are other ways to derive these formulas, but they take pages of derivations to go through. But that's the value of tensor calculus, that we come up with expressions that can be evaluated for any given coordinate system just by direct substitution. And that is a great example of how straightforward that is. Okay, now to normalize these expressions, again, we replace this with r hat, we replace this with r theta hat, and we replace c3 with r sine theta phi hat. And when we do, we get the normalized form that looks like this. We picked up a factor of r here and a factor of r sine theta throughout this term. So together, all of this makes up the normalized form. Okay, with that, we're done. We've derived the position vector, the velocity vector, and the acceleration vector for each of our sample coordinate systems.